Let's take a look at setting up a confidence interval for a mean. So to do that, we either need a set of data, or we need to know what is the number of elements in the data set, what's the mean of the data set, and what's the standard deviation of the data set. Now, to build the interval on top of that basic information, we also need to decide on a confidence level. So I'm going to run through how to set up a spreadsheet like this. So first, let's copy data and bring up a new sheet. So let's suppose I want to do a confidence interval and I have a set of data. First thing I need to do is get some summary statistics, like what's the count? What's the mean? What's the standard deviation? So I can use the count command to look in this column. As long as there's nothing else but data in that column, it'll count. It won't count words, only numbers. Mean, same idea, that's average. Average will ignore words. And standard deviation, depending on which version you use, this stdev will ignore words. If you use stdeva, it'll treat the word tip as a 0, which will screw up your standard deviation. So you can't select the whole column if you use version A of the formula. If I use the straight version for a sample, I can highlight. All right, so I have a standard deviation, I have a mean. Now these numbers have, what, 2 decimal places at most because they're dollars and cents. And so usually when we do summary statistics, we take it out 1 decimal place further. So I'm going to tone these numbers down a little bit. 3 decimal places. All right, so I got that. Next thing I need for given information is a confidence level. And let's suppose we went with the standard 95%. So 0.95. And you could leave that as a decimal or format it as a percent. Oops, wrong button. There we go. So once we have that, again, we're going to use the central limit theorem, which means we're going to have to calculate a t-score. Because in general, when you're working with means, you don't know the population standard deviation. If you did, you would use a z-score, but we're going to do it like most data where we actually don't know the population value for standard deviation. We just have a sample. So calculations I need to make is I need to figure out what the tail probability is. Now, it's always a good idea to draw a picture to get this started. So confidence interval, not for a proportion, but for a mean. And the procedure for a proportion isn't too much different. So we sketch ourselves a nice normal bell-shaped curve to the best of our artistic ability. And we want to place in the center here the mean. Now, if you're using z-scores, the mean is going to be 0. We have a confidence level of 95%, so that means 95% goes here in the middle. If I take 1 minus 95%, that gives me 5%. That's the value we call alpha. That's what the tails get to share in this case. So I need to know what alpha over 2 is. So that would be 0.025 or 2.5%. So that's what goes in each tail. So this area or probability out on that left side is 2.5%. And this right side is 2.5%. And what I want to know is what z-score goes with that. So typically with normal distributions, you plug in the z or x value and it spits out the tail probability. We're doing the inverse of that. So to calculate this z-score, we're going to use the norm inverse. That's what we would usually do. Okay. Now, problem with the norm inverse, it involves knowing the population standard deviation, which we usually don't know. So we're going to switch from a z to a t. And we're going to use the t inverse. So you always have to decide that, and it depends on the given information. T inverse wants 3 things. It wants to know what's the tail probability. It wants to know how many degrees of freedom you have, which is always n minus 1. And I believe that's it for t inverse. So for us, our t inverse is going to be sticking in the 0.025 tail probability. And then our n in this case was 157, so we're going to have a 156 when we make that count there. So I just want to kind of get an idea for what that's going to be. And looking at the picture. Now the T inverse always spits out a positive number. Positive, which is a little bit different than the normal inverse because it can spit out positives and negative. So the number it's going to return is actually this one, which is the opposite of the one on that side because T inverse is symmetric, like a normal function. All right, so making these calculations, I need to know what alpha is. So that's just equal to 1 minus the confidence level. Once I have alpha, I can calculate the, in this case, t-score. And the t-score is going to be the T inverse. So I start typing Ti, and it says, do you want the T inverse? I hit enter and say yes. It says, what's your probability? So it's not just alpha, but again, it's alpha over 2. So I'm going to grab my alpha value in cell C6 here, cut it in half. Wants to know how many degrees of freedom. And again, that's already kind of in the spreadsheet. So I just, here I'm arrowing up to the count, and then I just take 1 away from the count, and that's all it needs. Hit enter. So it gives me a number of 2.26, which seems reasonable. And the T inverse, since it depends on the count, for a 95% confidence interval, depending on how many data points you have, you'll get a slightly different number for T, even for the same confidence level. And that's an important distinction from T to normal. All right, so we've got our t-value. Next thing we want to do is use that t-value for our formula. So we're doing a mean, so the next important thing besides t is finding that error bound on the mean, also known as your margin of error. And it is your t-score times the standard deviation of the sampling distribution. Central limit theorem says the standard deviation of a sampling distribution is some either sample or population standard deviation divided by the square root of the sample size. So that's the formula we need to apply next. So back to the spreadsheet. So you really got to write things down on paper and use a spreadsheet. So next thing I'm going to calculate is the error bound on the mean, aka the margin of error. And that's going to be equal to the t-score times the sample standard deviation divided by the SQRT square root parentheses of the sample size. And enter. So I have a margin of error of 0.4-ish. And so interpretation here is that's like 44 cents because we're talking about tips for this average tip. That's what we're trying to calculate. So now that I have the margin of error, I can calculate the lower and upper values for my interval. So that's just going to be my mean minus the margin of error, and then the mean plus the margin of error. So I get that the average tip at this restaurant is somewhere between $3.41 and $4.29, if I round that up to the nearest cent. So we're 95% confident that the average tip is between $3.41 and $4.29. Another way I could state it is we're 95% confident that the average tip is about $3.85 with a margin of error of about 44 cents based on the error bound for the mean. All right, so we get a whole lot of information. This time we have to apply the central limit theorem, and we can use some formulas, in this case related to the t distribution, which is a sibling of the normal distribution. Thanks for your time. Have a good day.